Hello, my name is Adriana Namor, and I'm a PhD candidate at the Robotics and Vision and Medicine Lab at King's College London. Today, I will present our accepted work titled Semi-Automated Retinal Microsurgery Video Annotation with SAM2, Comparative Analysis of Prompt Strategies, conducted in collaboration with Moorfields Eye Hospital. Retinal microsurgery operates at micron-level precision, where even minimal deviations in tool positioning can cause retinal tears or detachments. Developing models that perform real-time surgical video segmentation is a prerequisite for intraoperative guidance and future robotic assistance. A significant barrier, however, is the extensive manual effort required to produce dense annotations for training, making efficient dataset generation strategies essential. Our goal is to evaluate how foundation models, like SAM2, can accelerate annotation while maintaining segmentation accuracy. We compared 3 SAM2 prompting strategies: single point, bounding box, and full mask, using 11 phantom retinal surgery sequences. From just 53 manually annotated frames, SAM2 propagated pseudo-labels across 2,333 frames, enabling large-scale data creation with minimal manual input. This figure illustrates our annotation pipeline. Manual keyframes are used to seed prompts, which SAM2 then propagates across entire sequences. The 3 prompting strategies generate 3 independent datasets: D1 using bounding boxes, D2 using manual masks, and D3 using single point inputs. Each annotated keyframe produces approximately 44 times more usable training labels through SAM2 propagation compared to manual labeling alone, enabling efficient dataset expansion while retaining accuracy. 4 segmentation architectures, UNet, DPLA v3+, TransUNet, and NNUNet v2, were trained on datasets generated by the 3 prompting strategies. Across all models, D2, the mask-based prompting strategy, consistently achieved the highest segmentation accuracy, with UNet reaching an MIOU of 0.713. The per-class IOU results demonstrate that D2 performs best in capturing fine instrument tips and subtle illumination boundaries. Qualitative overlays confirm sharper delineation of thin structures when using mask prompts. I will now show a brief sample from our inference video. This clip demonstrates segmentation running at 25 frames per second using a UNet trained on SAM2 propagated D2 labels, achieving the real-time performance required for intraoperative deployment. This study shows that foundation models like SAM2 can be integrated into annotation pipelines to efficiently generate training data for lightweight segmentation networks. These networks achieve real-time inference and address a critical clinical requirement in retinal microsurgery, where high-speed pixel-level feedback is necessary for surgical safety and precision. Ongoing work focuses on extending the pipeline to clinical videos featuring varied tools and conditions. Thank you for your attention. The QR code linking to the full paper and inference video is available on the poster. I look forward to discussing this work further at MICCAI's Ophthalmic Medical Image Analysis workshop.